Short on time, a little over. So we've got Ravi Singh speaking about RSVP-TE scalability.
Good afternoon. RSVP-TE scalability, or rather RSVP-TE usability at scale. Why am I talking about this topic here? I'm talking about this even though RSVP-TE has been around for a good 10 years, because of late there has been effort being made at various vendors to improve the RSVP-TE LSP scale. And as we do that, what are the operational issues that would come to the fore that need being addressed, and how would we address those issues? So basically, this presentation is going to be three-part. First is going to be a very brief, quick recap of what is RSVP-TE all about, very brief. Thereafter, I'm going to summarize the 6 different categories of operational issues that I believe make sense. And in the third part of the presentation, we'll walk through different ways to address those operational issues. And as with any such list, this list of operational issues may not be comprehensive. And if you think that some operational issues that you are encountering that are not addressed here, I would really look forward to receiving your comments on my email that was listed on the first slide. Okay, so RSVP-TE is a signaling protocol to set up LSPs, MPLS LSPs. It's been widely deployed for a while, and the key reasons why somebody would deploy that is to get traffic engineering and to get bandwidth accounting and admission control for your traffic, and also, importantly, fast failure protection, which basically is comprised of local repair as well as global repair following the local repair. And over the years, over the 10 plus years that RSVP-TE has been around, the networks have grown. As a result, the number of LSPs that are carried, the maximum number of LSPs that a specific router may carry has gone up. And as a result, issues that may have been minor annoyances in the past would have got magnified now. And with that said, let's look at what the 6 categories of issues are in using RSVP-TE, issues that are operationally relevant. So the first category would be, how do you configure a large number of LSPs? So typically when you have N routers that are hosting some MPLS-enabled service, there would be typically, in the most general deployment scenario, there would be a need to set up a full mesh of LSPs. And so we're going to look at the solution. I'm just capturing what would be the categories of operational problems. So that's the first category. Now, the second category is when you have a large number of LSPs in your network, when something goes wrong, how do you figure out what it is that's going on? And so it's basically, if you have, let's say, 100,000 LSPs on a given router, something goes wrong, looking through the CLI is like looking for a microneedle in a haystack. What would it take for that needle to jump out at you and tell you, basically the needle jumping out of the haystack? And so the third category would be issues around the use of auto bandwidth, which is basically, auto bandwidth is a feature which most vendors have, which is essentially LSPs that resize themselves based on how much traffic is entering the LSP, based on some analytics on the statistics for the LSP. And the other category would be, how would you utilize your network more efficiently? And so typically when you have RSVP P2P LSPs, sure, if you have a lag bundle between a pair of routers, sure, you can do load balancing over the components of the lag. But for a given P2P LSP between a pair of routers, you have the traffic going between a pair of L3 devices from the ingress to the egress. What would it take to use your network more efficiently? And what would it take to load balance more effectively? And then the other problem that's sometimes seen is that when due to some network churn, some links or nodes failing, when the LSPs are re-optimizing, you see data losses. Why do you see those? And what's a vendor-agnostic way to fix that even in a network where you have routers from multiple vendors? And of course, what I have listed here as the last category of operational problem would be, how do you in general reduce network churn in the context of RSVP-TE LSPs? So having looked at the three, or rather the 6 categories of operational problems, let's jump in and look at what it takes to solve each of those operational problems one at a time. So in doing that, I have this network diagram here. It's a pretty simple diagram, and I'm going to use this as an example to illustrate points as we go along. And so the routers numbered R1 to 8, think of them as PE routers that are hosting some kind of MPLS-enabled service, typically an L3 VPN or VPLS or whatever. And A, B, and C are your transit routers, and between R6 and C, there's a lag bundle. So if you have to configure LSPs between all of those PEs, R1 to R8, one way is to do it manually, which is, you have to configure the LSPs in each direction, which is onerous in terms of having to configure it. Now, there is already a way to address that problem, and it's our RSVP auto mesh. And before I get into that, so the solutions to these operational problems that I'm listing here, not everything is brand new. Some of this is stuff that has been around for a while, and for reasons maybe perhaps specific to the way various networks are set up, perhaps it's not getting used. There's other stuff that is right now in beta trials and not available to everybody to try out. And then there's stuff that's conceptually available but not implemented for lack of sufficient push from operators. So I would urge you, depending on if you find something interesting here, and I hope you will, the things that are not yet implemented, I would look forward to receiving feedback on, pushing to implement those. So back to RSVP Auto Mesh. So RSVP Auto Mesh essentially relies on creating RSVP LSPs not based on configuring each LSP individually. Rather, it relies on the availability of some BGP route learned from a remote router to trigger an on-demand setup of the LSP without having explicit configuration for that LSP. So for example, if you had an L3 VPN service in use in this network with the R1 to R8 being PEs, when R1 learns of some L3 VPN route from R5, that would be the trigger for R1 to create this LSP on the fly, and likewise for this mesh of 8 PEs. It's been around for a while, many customers use it, and what I would like to know is, for those of you that don't use it, and if you have specific reasons why you don't use it, please give us feedback. And let's move on. So when you have a large number of LSPs in the network, how do you figure out when something goes wrong? Like I said, figuring out from the CLI is very onerous. So in keeping with the telemetry theme, so here's LSP Telemetry. So essentially, what LSP Telemetry gives you is that from the router, you get some messaging coming at an off-router device that essentially is describing a subset of events that are happening on whatever LSPs that choose to be monitored this way, and what properties on those LSPs, how are the properties on those LSPs changing. So essentially, it has really 2 components. There's a collector, there's a transmitter, and the transmitter essentially, in the simplest form, the transmitter and the collector would have some kind of schema from which they would have generated code, and the transmitter is essentially sending off the events and properties to the collector. So an object model for LSP telemetry would look thus. A sensor would represent a source of data, and the sensor could be in the context of some resources, which could be 1 or more LSPs. And as part of the config, you would have a sensor and the resources that the sensor is in context of. And there would be an export profile, which is essentially saying how frequently is to send the data, and what transport protocol to use, and what serialization format to use. And then there's a server, the off-router device to which to stream this data. So the key thing here is, as compared to the CLI, you don't really have to look through everything. You can set your configs such that certain events, for example, LSPs going up or down, or events like a path error being received on an LSP, you could, as part of the sensor configuration in the events and properties registry, you could set up the config so that events that are more indicative of a grave failure bubble up to the top. So essentially, by having the right kind of configs for the critical events to be streamed out and having the collector side code have a way to visually represent this to you, the needle could essentially jump out of the haystack. Now the question is, how effective can we be in writing the collector side code, and how effective can we be in generating the config to ensure that the key needles are configured, what to spew out from the router to the collector. Okay, so auto bandwidth deployment issues. So like I said, auto bandwidth allows an LSP to resize itself based on sampling the volume of traffic flowing through the LSP at a certain, you sample periodically, and then after a much longer interval, you decide how the LSP needs to be resized. So when you have a large network where the number of LSPs is very large, so getting the sampling data from the data plane as to how many packets per second are flowing through the LSP, doing that on a querying basis does not scale. So you need a similar LSP statistics telemetry model where from the line cards, the LSP statistics themselves are getting streamed out from the line cards. They're streamed out, but to where? The collector for these statistics could be a component within the router created by the router vendor, or it could be an external device which is accumulating statistics. Now, the key benefit of pushing out these stats is that, firstly, there is no polling overhead, and secondly, this mechanism can be overloaded to have an off-router device do the computation for what should be the new size of this LSP. So essentially, an operator could have some code, whatever analytics algorithm you prefer to run, to decide what should be the new size of the LSP. So essentially, this gives you programmability in terms of running your own algorithms based on the sampling data to determine what should be the size of the LSP. Okay, now talking about maximizing network utilization. So the key things are, how do you spread the load? Spread the load in terms of how do you split the traffic for a given LSP over links that are getting not so well used. And that translates into two things, or rather two solutions. The first, what I would call as TE++. It essentially gives you the ability to set up an LSP, which from a configuration point of view looks like one LSP, but in the real network, it trickles itself into multiple sub-LSPs, and that essentially gives you a higher amount of total bandwidth for the LSP, even though there may not be an actual path through your network between a series of devices that has that much bandwidth. For example, in this diagram, so if every link in this network is a 100 meg link, and if there is, for whatever reason, a desire to set up a 300 meg LSP from R1 to R5, you could have an LSP on R1, which is one LSP from a management point of view, but in the network, it could actually be 3 LSPs of 100 megs each. And in this slide, the way I have shown it is, the splitting of the LSP is happening at the ingress, but it's not necessary that the splitting of the LSP happen at the ingress. The splitting could potentially even happen at the transit. And to facilitate that, for the splitting at the transit, the ingress would have sent some sort of association information as part of the signaling, so that at a transit router where the splitting is happening, it knows that these sub-LSPs are really part of the same LSP. So it would have ensured that the label it would have advertised upstream would be the same level for the 3 sub-LSPs. So from an actual signaling point of view, these would be 3 separate LSPs, but from a management point of view, these would be the same LSP. So what does it give for the operator? It gives the operator better utilization for their network. And even when you don't have a path which actually gives you the bandwidth you need for the LSP, by splitting up the LSP, you can get effectively the same. So now this slide is about how do you load balance your traffic So as we all know, load balancing of traffic, let's talk about a lag for a moment. So if you're load balancing some traffic over a lag, it relies on hashing on flow identifying fields in the packet. So the key invariant to be maintained is that all packets of a given flow go down the same link to prevent reordering. So entropy label, and this is an IETF standard, entropy label essentially gives you a way to carry the hash along with the packet. So when a packet enters an LSP, the ingress router of the LSP would hash on the flow identifying fields of that packet. And the flow identifying fields could be different based on what level of granularity you want for your flow. We'll get into that in a moment. So the ingress computes a hash, translates that into a proper MPLS label, sticks it into the packet behind a well-defined reserved label value of 7, and whichever transit router encounters this data packet, it does not need to look past the label stack to figure out its hash seed. The hash seed is there in the label stack right there. It can hash on the entropy label and get a load balancing outcome just as it would have if it had hashed on the inner flow identifying fields. So why is this important? Why is this interesting, really? So this is interesting because if you're running a network and you have a desire to load balance on finer granularity of flows. For example, if you're carrying, just as an example, you're carrying VXLAN traffic, and for whatever reason your traffic, that's the VXLAN traffic going over this LSP, for some strange reason, let's say your application that's using the VXLAN, it's not able to get the source port in the UDP header in the VXLAN encap to change for your your application specific flows. In that case, you don't have to worry about upgrading every single router in your network to understand the flow identifying fields on those very much inner headers. If you upgrade your routers at the edge so that the ingress can compute the hash by looking in as deep as you require, you're done. Your transit routers can continue to merely hash on just the entropy level. So that's really what entropy level gives you. And the other key thing is not every ingress-egress pair of routers in your network needs to be entropy level capable. So to elaborate on that, the pairs that are entropy level capable, they will use entropy level. The ones that are not, they will not. And the transits can handle both the cases. So for example, in this diagram, the traffic coming from R1 to R5, coming over the LSP from R1 to R5, R6 just needs to hash on the entropy level because R5 is entropy level capable. As a result, R1 would have inserted an entropy level. Okay, so moving on. So why do we see data packet losses sometimes when an LSP is re-optimizing? The key reason for that is that not every router in the world ends up advertising a label upstream after it has programmed the same in its data plane. So what that means is the ingress might, if this label propagation reaches the ingress before this transit router has managed to program that label in its fib, it's possible that this router might be seeing traffic for which it does not have a route, it'll drop it. So what's really the ideal way to do this? The ideal way for this to be done would be for every vendor to implement some sort of mechanism by which the control plane label advertisement does not happen until after the data plane is known to be programmed. But based on the way the world is right now, that's not really what every vendor does. So LSP self-paying is really a way to sidestep that problem and for the re-optimized instance of the LSP to not be made active at the ingress LER until after the data plane of the new instance of the LSP has been verified to be well programmed, all the way from the ingress to the egress. So how does it work? It works by essentially sending IP/UDP data probes over this new LSP instance so that they would exercise this new LSP's data path all the way. And if you get this, and by the way, the key thing about these probes is that the destination address in these probes is set to the IP address of the ingress of this LSP itself. So if these packets make all the way to the ingress, that means the data plane is programmed on all the routers. if this packet loops back to the ingress knows that the data plane is good and the traffic can be switched to the new instance of the LSP. So this is a way that data losses can be avoided during LSP reoptimization. And this is just a picture to essentially describe the same. The green LSP was the LSP that existed in the network, and the link between B and R6 failed. At that time, local repair kicked in between B and R6, and in response to having received an indication of this failure having happened, R1 initiates signaling for a new instance of the LSP, the red LSP, and it does not start to use this instance until after the data probe sent by R1 over this red LSP instance is received back. Okay, the last subcategory and how to address, or how to do better to address this problem. So when we are resignaling an LSP as part of make before break, now it is desirable to reuse the same label on every hop as long as the new path for the LSP is the same as the old path. When would that happen? That would happen typically when you're using auto bandwidth and you're setting up a new instance of the LSP with a higher bandwidth T-spec in that. And in that case, when your new path is the same, it really does not make any sense to blow away the old instance of the LSP and set up a brand new instance of the LSP on the same path with different labels, as that just tends to run into the same sort of issues that we saw that self-ping was addressing. So the key here is that, if possible, the egress should advertise the same label, or if you're using PHP, the penultimate hop router should advertise the same label as it was before. And a transit router, when receiving a label from downstream, should determine if the same label has been used by every router south of it for that LSP as was used for the prior instance of the LSP. If you do that, you should not, the churn caused by creating a brand new label in the network for that LSP would go away. The other thing is, when do you really resignal an LSP? If you're running a very large network and you're trying to set up a large number of LSPs at the same time, there'll be some propagation delay in the messages. And if you give up too quickly in regards to when you get your reservation message back, you can potentially exacerbate that problem, which was the original cause for why the messaging was slow to go. So the key here would be that unless the path has changed, unless there is an IGP update indicating that the path has changed, the router should just refresh the path message for the LSP without trying to tear down the previous instance of the LSP. And the last bullet on this slide is essentially talking about a problem that can happen when you have some network churn, some links going up and down, and you have LSPs with different setup and reservation priorities, and such that a less preferred LSP ends up getting preempted by a more preferred LSP that comes by later. So this essentially, the way to address this would be that, routers could be configured with some sort of, percentage config per setup priority level for the LSPs, so that when the bandwidth utilization downstream of that router on a given link is in excess of a certain configured percentage for that priority, that link not be used for LSPs at that priority. And by using these three subclasses of solutions, the network churn in setting up subsequent instances of RSVP LSPs can be reduced. And this slide is essentially just showing in the diagram the first sub-item that's listed on this slide, which is about reusing the label. And so basically, this is a case where the old and the new instance of the LSP are using the same path. And in this case, what essentially is being said is that all the way from R5 to to R1, it's desirable to reuse the same level to reduce churn. So in summary, this presentation has presented various solutions to these 6 subcategories of operational issues, and I believe they are eminently deployable. Some of these are already shipping, and some of these are in beta, and some of these exist as concepts but have not yet been implemented. For example, the TE++ splitting of LSPs at a transit router is not implemented yet by any vendor to the best of my knowledge. However, we believe it is desirable to implement it. We'd like your feedback on that. And also, based on the content that's been presented so far, it's my belief that it is very much possible to deploy RSVP LSPs at scale that are easy to configure, easy to monitor, LSPs that resize themselves, and that enable effective utilization of your network. And with that, I have a list of references, giving more detail about the things that we touched upon in this presentation. The last link is something that I did not yet touch upon in this presentation, because that's not really addressing any operational issue per se, but that's a series of recommendations that are more software implementation specific to make the scale go higher per se. And with that, I conclude, and any questions, please. Well, looks like everybody's ready to go home. Thank you.